When I was little, my father was famous. He was the greatest samurai in the empire.
Hey everybody, Jerry Williams aka Greater Sapien here. Thanks for stopping by. Some time ago, I put out a video about rockets working in space. It was a very simple video explaining things in a way a child could understand. Little did I know that that video would be such a magnet for conversation. For a video that only has 8,000 or so views, it's heading toward 2,000 comments, and a lot of people seem to want to comment on the topic. But also, some people want to comment on the topic a lot. Take Brian Hill, for example. Brian Hill has had some very long discussions on that comment page. Brian doesn't believe that rockets can work in space. He's not a flat earther per se, but he says the Earth is ontologically linear and not really a planet at all. I'm not sure if he even believes that outer space exists. I'm kind of afraid to ask, but he does believe that Jesus walking on water is a historical fact, so when he and I have exchanges, I don't do so with the illusion that I will be able to convince him of anything. No, discussing science with him is more of a fishing expedition for me. What can I learn about the way people like Brian think about these topics? What barriers in their understanding are they coming up against, and what questions does that cause them to ask? Because most likely there are other people who are genuinely curious about learning how things work, and seeing those questions answered may help them learn more. I say genuinely because I believe people like Brian are not genuinely curious about how things work. They are here to ask you questions 6 ways from Sunday in hopes that you'll make an error that they can call you on and then try to get a win. So I've had a number of long exchanges with Brian that have not gone the way he wished, and over the last several days, he's probably wondered if I've given up and he can claim victory. But when I decided to take up this hobby of YouTube videos again, I told myself not to make a hobby of the comment exchanges. So I told myself that any comment thread that I'm interested in enough to make a comment that takes more than 20 minutes to write up needs to become a video. Don't invest the time unless it works toward a video. You might wonder, why attack Brian Hill? Well, I don't see this as an attack. You see, unlike most that come at me on YouTube, Brian is actually intelligent, knows a little science, and because of that, he's a great example of the Dunning-Kruger effect. He doesn't know as much as he thinks he does, but he discusses it really well. So his questions are wide-ranging, and the answers are likely to help inform others. As I mentioned, my original video looked at the concept of rockets working in space at a level a child could understand. But oftentimes that leaves a little too much room for interpretation from those that are ill-informed or open deniers. So what I've done is I've gathered the claims Brian and others have made, the questions they've asked, and the things that I've inferred from their statements into one spot, and we'll spend some time going into detail about how rockets can work in space. I'm going to touch on a lot of things here, so I've tried to structure this according to the journey of the propellant, the fuel that makes the rocket move. It's what provides the thrust, so we're going to follow the fuel from one end to the other and touch on the related mechanisms and laws of motion involved as we go. So this is going to be a long one. Check the chapter markers for the points you are interested in. I said a moment ago that the fuel provides the thrust, but in order to do that, it must first combust. I stated in the first rockets video that rockets carry their own oxygen with them in space, so the fact that there is no air in space isn't a problem. But Brian Hill had an interesting take on that. He says I'm correct that rockets do bring their own oxygen, but everyone knows the experiment with the lit candle where you put a drinking glass over it and the candle goes out after the oxygen in the confined space is used up in just a few seconds. He says a rocket in space would go out even faster since it's going to shoot the gases away and the oxygen too, I guess. And that's thinking of a rocket in a way I never did, it seems. He's picturing the rocket as a container with a finite amount of oxygen, and when it's gone, the candle/rocket will go out. And he's not wrong. When the rocket is out of oxygen, it will go out. But he, like many others, doesn't understand how much oxygen the rocket actually has. Let's look at the candle example he presented. An ordinary candle is a mixture of hydrocarbon molecules that need a certain amount of oxygen molecules to burn. For example, every 2 hydrocarbon molecules may require 7 oxygen molecules to burn. In practical terms, it means in order to burn a 2-inch candle completely, a certain large volume of air is needed to provide enough oxygen. Chemical reactions are kind of predictable that way. This isn't a problem because air circulates and replenishes the local oxygen constantly and over the 2 hours that the candle burns itself away. Covering the candle with a glass restricts the candle to a tiny volume of air, which, as noted, it uses up in just a few seconds. When people say that rockets bring their own oxygen with them, it's not like with the candle. They don't just seal up the oxygen that happens to be surrounding the rocket and take it with them. If that was all they had, they would burn through that in less than a second. No, they know that they have a set amount of fuel and they know how much oxygen is required to burn up all of that fuel. Chemical reactions are quite predictable that way. They take that amount of oxygen in dense liquid form, and they carry that with them. The oxygen doesn't leak out into space because it's fed into the reaction at a specific rate. But not all rockets use liquid oxygen. Liquid O2 needs to be kept cold, and it's hard to do that for long periods of time, so that's best left for launch vehicles. You fill up the rocket and you go. Rockets that are already in space, like the Apollo moon landing modules, use what is known as hypergolic propellant. Hypergolic propellants are substances, a fuel and an oxidizer, that will instantly start to combust when they are combined. No need for an ignition system. You just put these things together and they go. A common pair is hydrazine and dinitrogen tetroxide. The dinitrogen tetroxide is a molecule that has a bunch of oxygen in it. Both of these substances are liquid at room temperature, and people can easily calculate how much each substance is needed to bring along. So, when we say rockets bring oxygen with them, we're not talking about bringing along some captured air. This is a calculated amount of stored liquid oxygen or oxidizer that is used in a controlled manner. Some people, most recently Beau Patah, have posited that since combustion chambers are open to a vacuum of space at the throat, it has no pressure. And when the liquid propellant is injected into the combustion chamber, it would instantly evaporate and not have time to be mixed and combust, because once the propellant is a gas, it will be evacuated out of the chamber into free space. Science deniers like to use absolute adjectives like instantly to eliminate the passage of time. But unfortunately, the passage of time does occur, and even though when exposed to a vacuum, a volume of liquid would instantly begin to evaporate, the process would take a considerable amount of time, and within milliseconds, these substances are going to combust. So that claim is off the table. Now we have combustion in the chamber. Liquid fuel is very rapidly being converted into a gaseous state. Doubters will say the combustion chamber is open to space, so any gases would evacuate out the throat of the engine into space. Usually they say the gas is sucked out because they perceive the vacuum of space as this active agent that takes action and sucks the gases into space. But a vacuum, to be very plain about it, is a volume filled with nothing, and as such, it does nothing actively. But what it does do is it allows. A vacuum allows.
The dude abides.
A particle is moving along, a vacuum allows it to do so unimpededly. The tragic crew over at Globebusters mentioned several times that the gases would instantly disambiguate into space, as if once the chamber is open to the vacuum, gases are practically teleported outside the container into space. We know from the practical use of vacuum chambers that this is not the case. As I mentioned this in the Globebusters video, that if gases were able to instantly expand with no restrictions into a vacuum, you wouldn't be able to repressurize a vacuum chamber slowly. The moment you cracked open the valve, the air in the room would fill the vacuum chamber to atmospheric pressure immediately. But that doesn't happen. Why? Because a vacuum doesn't suck. A vacuum allows. So what does this mean when it comes to gases being generated in a combustion chamber open to a vacuum? People will say, Okay, fine. You have a combustion chamber, but it's still open to a vacuum and won't be able to create pressure. Let's look into that. Here's a combustion chamber with one end opened to the vacuum. There's a volume of fuel here being energetically converted to gas. Let's say a particle of gas comes out with a velocity in this direction. Those that think the vacuum sucks will say the particle will get drawn out of the chamber like this.
All of that mass would be drawn out instantaneously, even without any thrust behind it.
But that would defy Newton's first law of motion. Yes, the first law of motion. When talking about rockets, the third law of motion is always featured prominently, rightly so. But all the laws of motion come into play at some point here. The first law says that this particle is going to keep going in this direction until something acts on it. A vacuum is nothing and doesn't act on anything. It allows this particle, this mass, to keep going wherever its path takes it. The only way to get out of the chamber is if it collides with something in such a way that their path takes them out. It's going to bounce around the inside of this container until it goes out the throat. It probably won't take very long, but it will take some length of time. When there are a bunch of particles generated at once or in a short period of time, they're all going to be going through that same process, bouncing around on their way out. But now there are a lot of them, so something else is going to happen. They're going to start colliding with each other. They will start interfering with each other's passage out into the vacuum. And the more reactions that occur in this chamber, the more collisions will occur, and the harder it will be to get out of the vacuum. The particles will start to get backed up trying to get out, and that is how pressure builds in the chamber. And as more collisions happen between the particles and the chamber walls, the pressure builds, more kinetic energy is added to these particles, and the higher velocity they are when they leave the chamber. Now that we have high velocity gases, how does that make the rocket, the craft, move? That's the big question, right? Because the particles of gas have mass and they have velocity, they also have momentum and create force when they collide with something. That comes from Newton's second law of motion. Now, the doubters watching might say, ha, you said when they collide with something, GS, the gases have to hit something and push off in order to transfer the force. That's why there has to be a medium like air or water or a wall to push off of. But no, that's wrong. Brian Hill is currently, well, as I was writing this script, blowing up the comment page, talking about how balloons are good analogies to rockets, even according to NASA. And balloons push off the surrounding atmosphere when air is rushing out, and that's how they are propelled, is his claim. To support his claim, he spent some time searching the internet for different websites talking about balloon rockets until he found two places that agreed with him. He found the Chemical Education Foundation out of Arlington, Virginia, which is a chemical industry group promoting education in chemistry that puts out educational materials for teachers to use. On one of their worksheets, they say that balloons push off the surrounding air and the ground. He also found Science World of Canada, which says the same thing on their balloon rocket page. I pointed out that they got it wrong, and that happens all the time when you're trying to simplify things for children and when you have people that aren't necessarily well versed in physics writing your copy. He feigned outrage that, well, they are lying to children then. And I say feigned because he actually thinks that the kids' websites are correct and that NASA is purposely hiding the truth. He found on a NASA website where NASA says that a balloon is a good analogy to a rocket engine, saying, the force of the air escaping is the action and the movement of the balloon forward is the reaction predicted by Newton's third law of motion. But he claims NASA is hiding the part about pushing off the atmosphere, unlike his other sources. I do want to note that the two sources he found have additional info on the balloon rocket pages. ChemEd mentions jets as a real-world application of Newton's third law, stating, the extremely high acceleration of the mass of gas creates a large force. Then, as indicated by Newton's third law of motion, an equal and opposite force, thrust, is created in the opposite direction of the released gas, propelling the jet forward. No mention of pushing off the atmosphere there. And Science World, directly after its error, states, the gas rushing out of the rocket or balloon is the action and the movement of the object in the opposite direction is the reaction. No mention of pushing off atmosphere there either. But Brian got someone that he feels is an authority to say what he wants to say, and NASA and everyone else is hiding the truth. Something tyranny. Anyway, how does high velocity particles going out the back end of the rocket or balloon translate into a forward motion of the craft? This is where the second and third laws of motion and the conservation of momentum come into effect. We all know the third law of motion as for every action there is an equal and opposite reaction. But the law is worded a little differently. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. And deniers will often focus on the two bodies part, asking, where's the other body that is interacting? Well, each individual particle of gas is a body, a mass, and the craft itself is a mass. It is the accumulated forces of these two-body interactions that cause the craft to move. Now, before I go on to the next step, there has to be an agreement. The particles in this high-pressure chamber have masses and velocities, and thus have momentum and exert force upon collision. This would be the case with a rocket in the atmosphere or a balloon in the atmosphere. If you don't agree that these particles have these properties, there's no going forward. Your universe does not operate under the same laws that mine does, and there's no way any of this will make any sense to you. But if you're in agreement with that, let's move on. Here's a simplified diagram of the forces on the inside of the combustion chamber. You'll see this often. I've used it myself many times. But I think it may be too simple. The idea is that these arrows represent the force of particles striking the interior of the chamber, or the balloon walls, and how the imbalance moves the craft. It usually is something like this. If this container was sealed off and a reaction was happening on the inside causing a pressure to build up, or you just pump it to a high pressure and sealed it off, there would be particles with mass, velocity, and momentum exerting force at all points along the interior due to collisions. But the container doesn't move because all the forces acting on the interior of the container are balanced with an opposing force. When a particle strikes at this point and bounces away, the force of the bouncing away tries to force the container in this direction. But at the same time, another particle is striking here, trying to force the container in this direction. So the container doesn't move. This happens at all points with all collisions, and the container stays still. The next step is to say that now there is a hole in this wall, and the particles can now escape out that hole. Most of the collisions on the interior are still being balanced by other collisions, and their forces canceled out, but now this portion of the container has forces hitting it, but the opposing side of the container does not. So now the container gets moved by the force of the particles striking it. And for many people, that's clear enough for them. But Brian Hill was having a hard time with how Newton's third was getting to the front end of the chamber. Where is the N3 occurring, he would ask. I got a hint of the issue he and others might be having as we discussed this with an analogy of a pressurized can. He mentions that molecules closest to the hole depart first, and the swirling nature of the inside of the container. And it got me thinking that people may see this and think that the particles over here are just leaving and are not seeing how them just dipping out the end affects everything else in the container. And I can see that confusion happening when you see these arrows and think, oh, this particle is just going out that way. But we have to remember from the Newton's first law that these particles are going to keep going in a straight path until something makes them go another way. And the only reason these particles are going this way is because they collided with something that made them go that way. Oh, I'm sure there's a 1 in a no billion chance that a molecule bursts out of the combustion fuel and had a straight path to the engine's throat and didn't collide with anything else. But all the other particles bounce off other particles and walls until that final collision that took them down the throat. That last collision that exerted force and imparted momentum this way did the same to the other body that way. And collision after collision happened until the sum particle in the chain of events for this last collision collides with the wall here. The forces that expelled these particles makes its way to the front end. That's how Newton's third law of motion takes effect right here. When I read that Brian wrote swirling nature about the inside of the container, I got the sense, which is only my inference, it's not what he wrote, that he and others picture particles meandering around, going back and forth, and then zipping out when the opportunity arose. But every time a particle alters from a straight path, changes velocity in any way, it's because it collides with something, either a wall or another particle. That's Newton's first law. Each collision is the mutual action of two bodies, Newton's third. And any collision that results in a force in this direction, the opposing force eventually makes it back here where Newton's third takes effect on the craft. That's not the only place where Newton's third law is applied, though, as this small area does not supply sufficient thrust. I'll explain why and where else Newton's third applies shortly, but now that I've introduced the transfer of the forces between the craft and the gases, I want to explain how the craft, like a rocket, doesn't push off an external medium and thus does not require one. It seems to me that the confusion deniers have stems from Newton's third law, its mention of two bodies, and deniers' misunderstanding of what constitutes a body. As I showed in the combustion chamber diagram, it is the impact of a particle, a body, a mass, with the interior wall of the chamber, a body, a mass, that creates the Newton's third interaction. When a bat hits a ball, the bat and the ball are the two bodies. When you push off a wall, you and the wall are two bodies. Someone might say, when a helicopter flies, the blades are a body and the air is a body. No, air is not a body. I will say that again. Air is not a body. Air is a collection of bodies. Each particle, each molecule that makes up the air is a body. I get the impression that the deniers think the air coming out of the end of the balloon, let's say, is a solid column of air that is pushing against the solid wall of air that is the atmosphere. That's not the case. No, the air that is coming out of the rocket, the air coming out of the balloon, is not a solid single body. And the atmosphere is not a solid single body. The particles that make up the rocket exhaust, the particles that come out of the balloon, are not connected together. The molecules that make up the atmosphere are not connected together. They only interact by colliding with each other. Now, a few minutes ago, I diagrammed out how the particles of combusting fuel impact the interior of the combustion chamber and effectuate Newton's third. The same goes for a balloon, by the way. But there are some like Brian who say that the air exiting the balloon is pushing on the atmosphere in order to move the balloon forward. Even now, as I was on my second day writing this script, Brian is basically declaring victory since I haven't responded to the thread. Since I haven't been responding, he's been convincing himself more and more that a balloon pushing off the atmosphere is the rocket slayer argument. He says a household balloon is pushed from about a 1 centimeter margin behind its nozzle where the air is escaping. But since we know that Newton's third requires the interaction of two bodies, how would pushing off the atmosphere work? Let's try to diagram that out. Here's a diagram of the balloon, which you can see is similar to the combustion chamber of the rocket. The main difference being that the gas in a rocket is trying to expand in the chamber, creating pressure, while the balloon walls are contracting, causing pressure. A particle of gas is bouncing around on the inside of the balloon, impacting the walls and other particles, and has a collision that sends it out the back end. Now I say the force from the impact with an interior particle that sent the particle out of the balloon has a corresponding force in the opposite direction that impacts the interior wall of the balloon, causing Newton's third. According to deniers like Brian, Newton's third happens when this particle collides with another particle somewhere here outside the balloon chamber. So we have this particle that has mass and velocity and thus momentum going this way. And it collides with an atmospheric particle that also has its own mass and velocity and momentum because every air molecule is moving all the time. So they collide, and Newton's third happens between these two particles right here, these two bodies. How does that force get to the craft in order to move it? None of the particles, the two bodies in the collision, are connected to the craft in any way, and they're going to go off in random directions. Unless something interacts with the craft body, no force transfer will occur. This can't occur by magic. The force doesn't get transmitted through quantum entanglement or something. So, I'm sorry, Brian, or anyone else who thinks the air leaving the balloon or rocket needs to strike something other than the balloon craft itself. But for Newton's third to happen, the actual craft or balloon itself has to be one of the two bodies involved. A collision out here just doesn't cut it. All right, the next thing we have to deal with is getting more thrust out of this rocket. As I mentioned before, the Newton's third interactions that happen here just aren't enough. And it's not like every particle that comes down the throat here comes straight through, leaving a force vector going right toward the front. No, particles will make their way down here from any direction, bounce around, colliding at every sort of angle, and even collide with a particle right here at the exit and deflect at a high angle like this. And unless it hits something, a mass going off in that direction is just a waste of momentum. So engineers give that particle something to hit. The nozzle. Particles hitting the nozzle get deflected backward, resulting in forward-pointing reaction forces, and Newton's third gets applied. With the addition of a nozzle, the rocket can capture a lot more kinetic energy from the escaping particles, and all this surface area is where the real thrust comes in. I wrote that part and then I remembered that Brian had a hard time with this image. Since its image is a simplification and Brian has a little knowledge and a desire for rockets to not work in space, he asks, but wait a minute, how does the force of a collision going up that way give you a force heading toward the front of the craft? It's another circumstance of oversimplification leaving too much room for deniers. So I have to explain that we're dealing with the impact at an angle here, and if you break up the force at impact into these XY components, you can see what's happening. For example, if you have an impact that is directly perpendicular to a surface, all of this force, which is in the y-axis direction, gets transferred to the surface in the y-axis direction, and the surface travels that way. But if the surface is angled, some of the force is in the y direction and some in the x direction, and the surface travels that way. We have all experienced this. So with the nozzle of the craft, we have impacts on this side with x and y force components, and impacts on this side with x and y components. These y-axis components are in opposition and cancel out, leaving these components here. So, there you have it. That's why rockets can work in space, right? You would think that that would be enough for someone who genuinely wanted to know how it works. But deniers like Brian Hill do not want to know that. They are seeking ways to deny it. They'll say, well, that makes sense, I guess, but how can work be done? Since the gases are able to freely expand into a vacuum, free expansion says no work can be done, which is true. But to be specific, the free expansion gas law says no work can be done outside the system. And the example always given for this is the closed volume with like a box with two chambers. One is pressurized with an ideal gas, and the other is a vacuum. There's a barrier between them. The free expansion gas law says if that barrier is removed, the gas on the pressurized side will freely expand to fill the entire volume. And since in the second stage, the number of particles has not changed, their speed, the number of interactions, and the total volume of the system has not changed from the first stage, this system can apply no work on the outside. The system is defined as the entire volume at the beginning, the pressurized volume and the vacuum volume combined. No work can be done outside of that. Work can be done inside the system, though. If you put a feather in the vacuum side, when that barrier comes down, the feather will get moved. We all know this. The system, when it comes to a rocket in space, is the rocket craft and its pressurized chamber and the volume of the vacuum, which is all of space in the known universe. So when the gases from the rocket are allowed to freely expand, it will be able to do no work outside of the known universe. Okay, but inside that volume, work can still be done. Thus, rockets can work in space. And you would think that would be enough to seal the deal, but no. Brian follows up by asking how this system can give itself momentum. And when I say that's not what a rocket does, he says, clearly it does, because the rocket is not moving, and then it ejects part of itself, and now the rocket has momentum. It gave itself momentum. And again, since I don't think Brian is unique in his misunderstanding, let me explain how the rocket as a system is not gaining momentum. A system is the sum of all the energy and mass in the scenario being looked at. There's a difference between the rocket as a craft and the system. The rocket craft is an object that you can walk up and touch. The rocket system includes all of the mass contained in the rocket craft and the fuel, and all the potential energy contained in the fuel, batteries, etc., and the momentum of the craft as well if it's drifting along. But let's call the momentum 0 if the craft is considered stationary. If the chemical reaction of the fuel causes momentum to be gained by a portion of the rocket system's mass in one direction, out the nozzle end, then an opposing amount of momentum in the other direction will have to be gained by the rest of the mass in the rocket system, so that the sum total of momentum in the system at any moment remains the same. The mass that is propelled out the nozzle is still part of the rocket system, even though now it is very far away. The system still has the same mass. Most of it is gathered in the craft of the rocket, but the system is the accounting of all the mass, not just the rocket craft. The system still has gained 0 momentum from what it began with. Yes, 0, because if you combine the momentum of the mass of fuel going out the nozzle and with the momentum of the remaining mass of the system going in the other direction, they cancel each other out. The rocket craft has gained momentum and is moving this way, but the rocket system as a whole has gained none. Conservation of momentum. Whew, I think that's it. I've gone from the initial combustion of the fuel to the application of Newton's laws and the conservation of momentum, which is more or less what I did for Brian Hill over the last several weeks. And you might think that that would have been enough, but truth be told, it was after I explained the conservation of momentum for a rocket system that he switched to talking about balloons pushing off the atmosphere. It was like the more information I provided, the more his understanding regressed into childhood. But I hope that's not what happened with you. I hope you found this informative, and I hope you'll be able to use this as a resource for those trying to understand the topic. So take care, everybody. This is the longest video I've done in some time, so I've really got to go.
That's my job! That's what I do! I don't lose! I win! Is there no one on this planet to even challenge me?
Maybe you came by to congratulate me on last night's victory.